All right, so get this. We all know machine learning models are amazing, right? But what if we could make them even better? Like way smaller, faster, more efficient. That's what we're diving into today.
Yeah, it's like we're souping up a race car, really looking for that ultimate performance.
Exactly. And the source material we've got here, it's like our roadmap to making AI even more powerful.
And it's not just about raw power, it's about accessibility, too. Imagine these super advanced models, but they're running smoothly on something as small as your phone.
Oh, that's what I'm talking about. No more battery drain. So our first pit stop, I guess, is model compression, which kind of sounds intense, like squeezing a massive AI into a tiny box.
Well, if you want a powerful AI on your phone, you need to make it fit, right?
Right.
And one way to do that is with something called knowledge distillation.
Okay.
Imagine taking a super smart, giant AI model and creating basically a mini-me version of it.
So the smaller model, it basically learns from the big one.
Exactly. It learns to mimic the bigger model's predictions, but it's way more compact.
It's like distilling like a brilliant professor's knowledge into a really good study guide.
Perfect analogy. And what's amazing is this mini-me AI, it can often perform almost as well as the original, especially for specific tasks.
So things like real-time language translation on our phones, is that how that works?
Exactly. All that intelligence packed into a tiny package without your phone, catching fire.
Love it. But okay, our source material mentions other ways to shrink models too. What about quantization? That sounds like something from Star Trek.
Haha. Yeah, it sounds complicated, but the idea is pretty simple. Imagine saving a picture, but in a smaller file format. You might lose a little detail,
Right.
but the file is way smaller. Quantization is kind of like that. We make the numbers the model uses less precise.
So it's a trade-off. A little less detail for a much smaller side.
Yeah, exactly. Like finding that sweet spot between image quality and file size.
Okay, I'm getting it. And I guess that makes a huge difference for things like image recognition or all those language processing apps we use.
Absolutely. Smaller model, faster processing, longer battery life, wins all around.
This is making me think about all the digital clutter I have on my phone right now.
Haha!
Speaking of clutter, what about pruning? Is that like deleting old files we don't need anymore?
It's a great way to think about it. Pruning is like spring cleaning for your AI. You go in and remove connections in the model that aren't actually doing anything useful.
So streamlining, getting rid of the dead weight.
Exactly. You end up with a leaner, faster, more efficient model.
I'm starting to see just how much work goes into making these models as efficient as possible. It's like optimizing every single line of code.
Pretty much.
I'm guessing low-rank factorization is another one of these optimization tricks.
You're catching on quick. It's a little more math heavy, but the basic idea is simplifying complex parts of the model, breaking down a tough equation into smaller, more manageable chunks.
Gotcha. I can appreciate the concept even if the math's a bit over my head. It's all about finding clever ways to simplify things without losing the important stuff.
Exactly. And finally, there's weight sharing, where different parts of the model actually reuse the same components, like building multiple houses with the same blueprint.
Oh, that's efficient. Avoiding reinventing the wheel every time.
Exactly.
Okay, so we've covered a ton of ground already in model compression, shrinking those massive models down, making them lightning fast and super efficient. But then how do we make them learn new things quickly? That's where transfer learning comes in, right?
Right on. Think of it this way. You've trained a champion chess player.
Okay.
Now you want to teach them poker. Do you start from the scratch?
Well, no. They already understand strategy, right?
Exactly. They already have the foundation. And that's what transfer learning does. It takes a model that's already learned a lot of information and uses that knowledge for a new task.
So it's like giving our AI a head start.
Yeah, like a shortcut to success. And this has been a game changer, especially in things like computer vision or natural language processing. We can train new models way faster.
Now we're talking. It's like we're assembling an AI dream team. We've got our lean, mean, compressed models, and now we're giving them a boost with transfer learning. I'm guessing there are different flavors of transfer learning, though, right? What's feature extraction all about?
Think of it like using a pre-trained model as a superpowered magnifying glass. Let's say you want to build a model that can identify different types of flowers.
Okay, I love flowers.
Instead of training a brand new model from scratch, you can use one that's already learned to recognize tons of images. This pre-trained model can extract all sorts of useful info about the flowers, like their shapes and colors, all those details.
So it's like our flower identifying model is getting insider tips from a botanical expert who's seen it all.
Yeah, and that becomes the starting point for our new model, saving us a ton of time and effort.
Now that's efficiency. But what about fine-tuning? Is that like giving our model a personalized training regimen?
Absolutely. We take that pre-trained model and adjust it specifically for our new task. It's like having a personal trainer who helps tweak your workout to hit your specific goals.
I love these analogies. So with fine-tuning, we're taking that general knowledge and making it super specific to what we need, right?
Exactly, which is especially useful when we don't have a ton of data to work with in the first place.
Which is all starting to make sense. But are there ever times when transfer learning, isn't the best approach? What if the new task is totally different from what the model already knows?
That's a great question. If the new task is too different, transfer learning might not be that effective. It's like trying to, I don't know, use your basketball skills to play baseball. There might be some overlap, but you still need to learn a whole new set of moves.
Makes sense. Now, our source material mentions a few other types of transfer learning too. What's domain adaptation? It sounds kind of cloak and dagger.
Haha, it's about bridging the gap between different types of data. Let's say you have a model that's been trained on news articles, but you want to use it to analyze, say, social media posts. The language people use in those two places, it can be pretty different.
Oh yeah, totally. So we'd have to teach our model to understand the slang and all the internet lingo.
Exactly. Domain adaptation helps the model adjust to those differences, making it more accurate and reliable in the new environment.
Gotcha. Okay, now this next one sounds like something straight out of sci-fi. Few-shot learning. Are you telling me we can train a model with just a handful of examples?
It might sound too good to be true, but few-shot learning is definitely pushing the boundaries of what's possible. It's all about enabling models to learn new tasks from very limited data, kind of like how humans can.
So, like showing a model just a couple pictures of a platypus and expecting it to be able to spot any platypus from then on.
Yeah, it's surprisingly effective, especially with new techniques like meta-learning, which is like giving the model a set of tools that help it learn new things super fast.
Mind blown. And then there's zero-shot learning. That sounds even more futuristic. Is that even possible?
It's the holy grail, really, getting models to perform tasks they've never seen before. It's still very much a work in progress, but we're making progress. Imagine a model that can identify a new type of fruit just based on its knowledge of other fruits, even though it's never seen this specific one before.
That sounds like pure magic.
It might seem magical, but it all comes down to teaching models to understand the underlying principles, the relationships between things.
So instead of just memorizing facts, they're learning to think for themselves.
Exactly, and that's a key step towards creating truly intelligent AI.
Okay, we've covered so much already and my head is spinning. We've shrunk our models, made them super learners, and now it's time to fine-tune them for peak performance, right? What's next on our AI optimization journey?
Now it's time to get under the hood and really fine-tune these models for ultimate speed and efficiency. It's like taking that souped-up race car to the best mechanic in the world for those final adjustments.
I am so ready for this. Let's start with gradient accumulation. It sounds pretty technical. What's the basic idea?
Imagine you're trying to move a huge pile of sand with a wheelbarrow. You can only carry a small amount at a time, right? But you can make multiple trips. Gradient accumulation works kind of like that. It lets us train models with larger batches of data, even if our hardware can't handle it all at once.
So it's like breaking down a big task into smaller, more manageable chunks.
Precisely. And this is super helpful when we're working with limited resources because we can train more efficiently without sacrificing performance.
Smart. Okay, our source material also talks about mixed precision training. What is that?
Think about it like using different units of measurement for different jobs. Sometimes you need super precise measurements, like when you're baking a cake.
I'm a terrible baker, so I get that.
But other times, you don't need to be so precise, like if you're estimating how far away the grocery store is.
Right.
Mixed precision training uses lower precision numbers for some parts of the training process, and that makes it faster and more efficient.
So we're basically streamlining the process without losing the essential information.
Exactly, and this can make a huge difference in speed, especially when we're training on special hardware like GPUs.
Okay, all these pieces are starting to fit together. Now, what about batch normalization and layer normalization? What do those do?
These are all about balance. They help make sure all the different parts of our model are working together smoothly. Think of it like adjusting the volume on different instruments in an orchestra so everything sounds balanced and clear.
Ah, so we're preventing any one part of the model from being too loud or too quiet.
Exactly, and that helps us train the model more effectively and avoid problems down the road.
I'm starting to see just how much goes into creating a really top-notch AI. But I am curious about how we train those supermassive models that are too big to even fit on a single machine. What happens when our AI, outgrows its garage?
Great question. That's where we move into the realm of model parallelism and scaling. This is where things get really interesting because now we're talking about training models that are spread across multiple GPUs or even entire networks of computers.
Whoa. We're playing in the big leagues now. It sounds like coordinating a massive construction project.
Great analogy. And just like in construction, there are different ways to divide and conquer. One approach is called model parallelism.
Okay?
We split the model itself across multiple GPUs.
So it's like taking a giant blueprint and dividing it up so different teams can work on different sections.
Exactly. And this allows us to train models that are so big they wouldn't even fit on a single GPU.
This is starting to sound like we're building the Death Star of AI. What other ways are there to tackle this training process?
Another approach is data parallelism.
Okay.
We divide the data itself across multiple GPUs. It's like having multiple chefs working together to cook a giant feast. Each one focuses on different dishes.
Instead of one chef trying to do everything at once.
Right, and this is super efficient for speeding up training, especially when we're dealing with massive data sets.
There must be a lot of coordination involved to make sure all those GPUs are working together properly.
Yeah, it's like conducting an orchestra. You need to make sure everyone's playing in sync. And then there's pipeline parallelism, which is a little more complex. Imagine an assembly line where different workers specialize in different tasks.
So each GPU is like a specialized worker on our AI assembly line.
You got it. And this approach can be very efficient for using hardware and saving memory. We're basically building a super efficient AI factory.
This is blowing my mind. It sounds like model parallelism is essential for training those cutting-edge AI models that are doing those incredible things we see in the news. But let's shift gears for a minute and talk about a different frontier in AI semi-supervised and unsupervised learning. What's all the buzz about these approaches?
Semi-supervised and unsupervised learning are all about unlocking the potential of all that unlabeled data out there. Think of it like this. In the world of AI, labeled data is like having a super detailed instruction manual.
Right, it tells the AI exactly what it's looking at and how to classify it.
Yeah, but what if we don't have that instruction manual? What if we only have the raw ingredients, the data itself?
So it's like giving the AI a box of Legos with no instructions and hoping it figures out how to build something amazing.
Exactly. It's definitely a challenge, but that's what makes it so exciting. With semi-supervised and unsupervised learning, we're teaching models to learn from unlabeled data.
Wow. So to find patterns and structure on their own without any explicit instructions.
Precisely. It's like giving the AI a sense of intuition and discovery.
I love it. Okay, what are some of the ways we do this? What's self-supervised learning all about?
It's like giving the AI a puzzle to solve. Imagine taking a sentence and blanking out a word at random.
Oh, like a fill-in-the-blank exercise.
Yes. And we ask the AI to predict what the missing word is based on the other words in the sentence.
So the AI has to use context clues to figure it out.
Right, and by doing this over and over, the AI starts to learn the structure and meaning of language, all without needing labeled data.
That's incredibly clever. What about contrastive learning?
Contrastive learning is all about teaching the AI to distinguish between things that are similar and things that are different, like showing a child a bunch of pictures of cats and dogs and asking them to sort them into piles.
Oh, I see. So the model is learning by comparing and contrasting.
Exactly. And by doing that, it starts to build an understanding of what makes a cat and a dog, all those defining features.
I'm really starting to appreciate just how powerful these techniques can be. It's like we're giving AI the ability to learn from the world around it, just like we do. But I am also really interested in those approaches that are pushing the boundaries of AI even further, things like reinforcement learning and meta learning. What can you tell me about those?
Reinforcement learning and meta learning, those are all about taking AI to the next level. They're about creating AI that can learn continuously, adapt to new challenges, and even learn how to learn itself.
Okay, now this is where it gets truly mind-blowing. Let's start with reinforcement learning. Whenever I think of reinforcement learning, I always picture like teaching a dog a new trick.
That's a perfect analogy. In reinforcement learning, we have an agent, and it's learning through trial and error.
Okay.
Just like that dog learning to sit or fetch. It interacts with its environment, gets rewards for good actions, penalties for the bad ones.
And eventually it figures out how to get the most rewards, right?
Exactly. It learns how to achieve its goals. And this has led to some incredible breakthroughs.
Like what?
Well, think about AI that can beat world champion Go players, or robots that can navigate super complex environments.
So reinforcement learning is all about learning by doing, huh? What about meta learning? What makes it so special?
Meta learning, sometimes called learning to learn, is all about training models to adapt to new tasks really quickly, even with very little data.
So we're not just teaching AI to do one thing, we're teaching it to be a fast learner.
Exactly. It's like giving our AI a set of learning superpowers.
That's a game changer. So how do we actually do this? How do we make AI learn how to learn?
Well, one popular approach is called model-agnostic meta-learning.
Okay, that's a mouthful.
It's often called MAML for short.
Okay, that's better.
And it involves training the AI on a bunch of different tasks, but each task only has a small amount of data.
So it's like giving the AI a sampler platter of different subjects. A little bit of math, a little bit of history, that kind of thing.
Exactly. And the goal is to find those settings within the model that let it adapt quickly to any of those tasks, even with just a few examples.
It's like giving the AI a mental toolbox filled with all these adaptable skills.
That's a great way to put it. And the cool thing about MAML is that it can be used with tons of different types of AI
It
models.
sounds like meta learning is still early days, but the potential is incredible. I can't wait to see where this goes. But for now, let's talk about how we actually use these advanced AI models out in the real world, especially when you're dealing with like mountains of data and all these complex systems.
That brings us to the world of federated and distributed learning. These are the tools we use to handle the challenges of scale and privacy in this age of big data.
Okay, so we've got these amazing AI models, but training them on huge data sets is a whole other beast, right?
Exactly. That's where federated and distributed learning come in. They let us train models on gigantic data sets that are often spread across many different devices without sacrificing anyone's privacy.
This sounds like the ultimate team effort for AI. What's the difference, though, between federated learning and distributed learning?
Think of it this way. Federated learning is like a global research team.
Okay.
Scientists from all over the world are contributing their findings, but they never share their raw data with each other. It's all about protecting privacy while still harnessing the power of a huge pool of knowledge.
So each device or server is like a little research lab, contributing its own unique piece of the puzzle.
Perfect analogy. And a good example of this is how your smartphone can help improve things like voice assistance without actually sending your voice recordings to the cloud.
Oh, so all the training happens right on my phone.
Exactly. It never has to leave your device. It's all about collaborating without giving up your private information.
Wow, I can see how powerful that would be, especially in fields like healthcare.
Oh, absolutely. Imagine being able to train an AI model to diagnose diseases using data from hospitals all over the world.
And you wouldn't even have to move all that sensitive patient data around.
Exactly. You'd protect patient privacy while making major advances in healthcare. Now, distributed learning is a bit different.
Okay.
It's more about tackling the sheer computing power you need to train really huge AI models on massive data sets.
So it's like building a super brain for AI training by connecting a bunch of smaller brains together.
Exactly. And this is crucial for training those cutting-edge models that are, pushing the limits of what we thought was possible.
It's like we have these two different tools for the job. Federated learning is all about privacy and collaboration, and distributed learning is about raw computational power.
You got it. And both of them are essential for making AI more powerful, more accessible, and ultimately more beneficial for all of us.
This is incredible. We've gone from shrinking models to making them super learners, and now we're training them on a global scale. It's mind-blowing to think about what the future holds.
It is, and this is just the beginning of our deep dive.
Stay tuned.
So, we were talking about making AI more efficient and adaptable, and there's this technique called reinforcement learning from human feedback, or RLHF, that really pushes things forward.
RLHF, it sounds kind of intense, but I got to admit, the idea of AI learning directly from us, from human feedback, is pretty fascinating.
It's like having a personal AI coach, guiding the model to make better choices, but based on what we humans think is best.
So instead of just using all that data, we're adding in some, I don't know, human wisdom to the mix.
Exactly. It's super useful when we're dealing with those tasks that are really hard to define with like specific rules. How do you teach an AI to be helpful or harmless or even understand human values?
Yeah, that's tough. It's almost like you're trying to code in empathy. So how does this RLHF thing actually work? Are we talking about people like sitting there and grading every single thing the AI does?
It can involve that, but it's usually more subtle. Think about those large language models like ChatGPT.
Okay, yeah.
Developers can use RLHF to kind of fine-tune those models based on feedback from real people. How safe are the responses, how helpful, how relevant, all that.
So it's like having editors giving feedback on a rough draft. They're helping the AI learn to write better, more human-sounding text.
Perfect analogy. And it highlights how important that human touch is, especially as these models become more and more advanced.
Yeah, it makes sense. Especially for things like those virtual assistants or chatbots, we want them to be helpful and fun to talk to, not like robotic or annoying.
For sure. The whole point is to build AI that really understands us, that gets what we need.
Okay, RLHF is officially on my radar now, but our source material also mentions this thing called meta-learning, and honestly, that sounds even more mind-boggling.
Meta-learning is like giving AI the ability to learn how to learn.
Whoa, hold on. Are you saying we can create AI that can teach itself, like some kind of, I don't know, AI genius that picks up new skills super fast?
Well, it's not quite self-awareness yet, but it's a huge step in that direction. Think about it this way. You learn to ride a bike, right?
Of course, everyone learns to ride a bike.
Well, that experience, it gave you more than just bike riding skills, right? It helps you learn other things too, maybe skateboarding or snowboarding. You built up this sense of balance and coordination, stuff you could use for other things.
Okay, yeah, I see what you mean. So meta-learning is giving AI that same kind of ability to take what it's learned and apply it to new things.
Exactly. And it has the potential to completely change how we approach all sorts of problems.
So we're not just showing AI how to do things, we're showing it how to be a super learner.
You got it. And that's a game changer. So how do we actually make that happen?
Yeah, how do we do that?
Well, one approach that people are listing is called model-agnostic meta-learning, or MAML.
Mammal. Okay, I like that. It's catchy.
It is, and it basically involves training the AI on a bunch of different tasks, but with just a little bit of data for each one.
So it's like giving the AI a taste test of all these different skills.
Exactly. A little bit of this, a little bit of that. And the goal is to find those model settings that allow it to quickly pick up any of these new tasks, even with just a few examples.
So it's like giving the AI a Swiss Army knife of skills ready to tackle anything.
I like that. A mental toolbox ready to go. And the cool thing about MAML is that it can be applied to lots of different types of AI models.
This meta-learning thing, it sounds like it's still early days, but the potential is just huge.
For sure. But let's shift gears a bit and talk about how we use these super advanced AI models in the real world, especially when you've got those mountains of data and complex systems.
Yeah, how do we take all this amazing potential and put it to work?
That's where federated and distributed learning come into play. They're all about solving the challenges of, massive scale and keeping things private in our data-driven world.
Okay, we've got these powerful AI models all ready to go, but I'm guessing training them on those massive data sets is a whole other ballgame, right?
It is, but that's where federated learning and distributed learning come in. They help us train models on those huge data sets, which are often spread out across tons of different devices or servers without anyone's privacy being compromised.
So this is like a giant AI team effort happening on a global scale.
You got it. So what's the difference between these two approaches? Well, think of federated learning like a worldwide research project.
Okay.
You've got scientists from everywhere contributing their discoveries, but they're not sharing their raw data. It's all about protecting privacy while still tapping into a massive amount of knowledge.
So each device or each server is like its own little research lab, adding its piece to the bigger picture.
Exactly. And a really good example of this is how, your smartphone can help improve things like voice assistance.
Right, right.
But it doesn't have to send your actual voice recordings to the cloud. The training can happen right there on your phone.
So it's like my phone is whispering its knowledge to the AI without ever revealing my private conversations.
Precisely. Collaborating without compromising privacy.
I can see how useful that would be, especially in places like healthcare, where privacy is so important.
Definitely. Imagine training an AI model to diagnose diseases using data from hospitals all over the world, but without ever actually having to collect all that patient data in one central place.
That would be a huge breakthrough. Okay, so what about distributed learning? How is that different?
Distributed learning is more about dealing with the sheer computational muscle you need to train those massive AI models on gigantic data sets.
So we're talking serious computing power here.
Oh, yeah. Think of it like building a supercomputer just for AI by linking together a bunch of powerful machines.
It's like building a brain trust for AI training.
That's a great way to put it. And this is essential when you're training those cutting-edge models that are really pushing the limits of what AI can do.
So it's like we've got these two different approaches, each with its own strengths. Federated learning is all about privacy and collaboration, while distributed learning is about pure processing power.
Exactly. And both are key to making AI more powerful, more accessible, and more useful for everyone.
This is amazing. We've gone from making those AI models smaller to teaching them how to learn like pros, and now we're talking about training them on a global scale. It's mind-blowing.
It is, and we've only just scratched the surface. There's so much more to explore.
Welcome back for the final part of our AI optimization deep dive. I don't know about you, but my head is still spinning from all the amazing stuff we've learned. We've shrunk our models, made them super learners, and even figured out how to train them on a global scale. But now I really want to know, where is all this leading? What's next for AI?
Well, get ready, because we're going to explore the frontiers of AI and the exciting possibilities these advancements unlock.
I'm ready. So what kind of impact are these techniques having in the real world right now?
One area where we're seeing huge progress is personalized medicine.
Oh, wow, that's exciting.
Imagine, an AI that can analyze your genes, your lifestyle, even your medical history, and create a treatment plan that's completely customized for you.
So it's like having an AI doctor that knows you better than you know yourself.
It's not about replacing doctors, but about giving them incredibly powerful tools. AI can help identify risks, predict how you might respond to different treatments, even suggest new options that nobody thought of before.
That's amazing. Are there other fields where this is having a big impact?
Oh, absolutely. Think about materials science. AI is already being used to discover brand new materials, stuff with incredible properties, like, super strong but lightweight alloys or solar cells that are way more efficient.
So we're talking about materials that could revolutionize all kinds of industries.
Exactly. Everything from how we build things to how we generate energy.
I'm starting to realize that these AI techniques, they're not just about making AI better. They're about using AI to make a better world.
That's a great point. And another area where AI is making a big difference is in drug discovery.
Okay, how so?
Well, developing new drugs has always been this long and expensive process.
Yeah, it's notoriously difficult.
But AI is changing that. It's helping scientists find those promising drug candidates way faster and more efficiently.
So we're talking about AI that could help us cure diseases and create life-saving treatments.
That's the hope. AI can analyze massive amounts of data about diseases, genes, all those potential drug compounds to zero in on the most promising directions for research. This could speed up the development of new therapies for so many diseases.
This is incredible, and it gives me so much hope for the future. It really sounds like AI has the potential to solve some of humanity's toughest problems.
It does, but we also have to remember that AI is a tool. And just like any tool, it can be used in ways that are harmful.
That's a really important point. As these techniques get more and more powerful, how do we make sure that they're used responsibly and ethically?
It's a question we all need to be thinking about. We need to have those tough conversations now to figure out the ethical guidelines for developing and using AI. And we need to make sure that everyone has a voice in that conversation.
So it's not just about the technology itself, it's about making sure that it's used for good.
Exactly. We have to think carefully about the consequences and make sure that AI is aligned with our values as humans.
This is so much bigger than just lines of code and algorithms. It feels like we're on the verge of a new chapter, not just for AI, but for humanity's relationship with technology.
I think you're right. And it's a chapter filled with amazing possibilities, but also real challenges that we need to face head on.
Well, this has been an incredible journey. We've really explored the cutting edge of AI, and honestly, I'm walking away with a mix of excitement and a sense of responsibility.
That's great to hear. It's important to be excited about the potential, but also to keep a critical eye on how it all unfolds.
Absolutely. So, as we wrap up our deep dive, what's the one thing you really want our listeners to remember from this conversation?
I hope they come away with a deeper understanding of how quickly AI is advancing, how it's already making a difference in so many areas, and how important it is to be part of the conversation about AI ethics.
I couldn't have said it better myself. The future of AI is something we all have a role in shaping. Thank you for taking this deep dive with us into the fascinating world of AI optimization and adaptation. Until next time, keep exploring, keep questioning, and keep learning. 27C.